Uh, Hello. So I'd like to tell why I think that we are very close to getting deeper in physics thanks to AI, not solving, but just going one level deeper. So from one side, there are many claims of theory of everything, but they get some likes on social media, but they are basically ignored by mainstream, while the verification is extremely difficult, require really tough simulations. And now AI can automatically build such simulations and test various agreements, what it has already started. So I think all these claims soon will be rigorously verified. And if one of them is successful, they develop into working theory. If none, then AI could further search through possibilities, maybe combine, look at some population of models, Lagrangians, to finally find the final model. So I think it's a matter of months now. So first of all, why we need deeper physics? Yeah. So from one side there are many problems with current ones, like this basic unification with gravity of standard model, then dark matter and many others. From the other, there is complexity. Now you have this gigantic Lagrangian I'm showing in a moment, which was found by guess and fit. Yeah, so some previous didn't work, so they guessed new terms and fitted them. So it sounds like new epicycles, like these hundreds of years ago that didn't work. So we add more corrections and more, but we don't understand what's happening there. Yeah. Moreover, there are like 30 parameters of standard model, so we should get deeper. We should smaller. Like we should get it down to a few, like 3 or something. And it is all no longer effective. That the current standard models use as effective model that we treat particles as perfect points. While we know that particles are field configurations and like electromagnetic of electron, we don't really understand now. So we would like to get deeper to this field, building particles, look at this evolution. So decay of particles should be evolution of this field deeper. So and indeed, we will get we are very close it. I will show some simulations from Fable getting this kind of decay of muon, for example. So there were many these physics LLMs with thousands of Zenodos, Warsalas. I've tried to look at some, but it's not in Dublin. Fortunately, now the modern LLMs are able to do much more important tasks here, like objective verification, like AI agents building simulations, running them, testing agreements with various properties of physics now, yes, until getting full agreement. Like the most important charge quantization that naively electromagnetics gives charge, which is real number, while in nature is integer, and so on. We need to explain it finally because mainstream like only standard electromagnetics doesn't explain it. Okay, so there are like 21. So there is at least one such environment. It's OpenWave on GitHub. One can also add on model. It tests like 21 criterions, like discharge quantization. And so there are like multiple moments currently. So this is the current benchmark kind of arena of models, you can say. And so the most important is validated that indeed we need something like charge quantization, and the model has these properties. Maybe some partial that something works, maybe a matter of improving the model, maybe a better simulations. Unless negative is the disqualification theory of model. Yeah, so that we know that our model says one, but we see that physics says something different. So it says that it's wrong, but maybe the author could modify it somehow to repair it, to make it work. Maybe inspire from the different model which is able to get this property. Then some in progress planned, so maybe it could be too difficult to predict in this moment, but maybe for so I think this is the goal. This is, I think, the first this kind of environment, but there should be more. I think all these theory of everything claims should be verified rigorous this way. And if not successful, we should search further. AI could try to modify these models, find the better ones. So they are open. I also encourage to build more such benchmark and adding more models. Also, I to talk more about this most promising currently, this liquid crystal approach, and why it's so difficult. Yeah, so that Lagrangian looks simpler, but its consequences are extremely difficult. Okay, so here is this standard model Lagrangian. Yes, it's huge. Yeah, so like epicycles, previously it works. So they guessed new terms, fitted their parameters. So it says we don't understand what's happening there. Yeah, so we'd like to get deeper and try to derive it from some more compact Lagrangian. So it has 30 parameters, while the one like this one has like 3. I'm mentioning in a moment, and there has many problems like this problem with compatibility with gravity. There is very nice EMC problem. There is EMC effect that they say that proton neutron has 3 quarks. But if you ask about nuclei and try to also see them as back of quarks, it doesn't work. The experiments say completely different. So we don't know. The simplest nuclei are not explained completely from perspective of QCD. So so they always say that in 20 years it will work. I don't care. I've tried to many such discussions. They don't understand. I think there are essential qualitative differences we need to include to move forward, not just saying that in 20 years it should work. So especially nuclei, we don't understand nuclei currently. If there are three nucleons, then they need three body forces. If there are 4, we then need 4 body forces. So this is just some Taylor expansion. We don't know what's happening, but we can fit formula for that. Yes, again, so we can build models, describe what we see, but we don't understand what's happening. Yeah, so we should get deeper to understand, also to resolve the problems current. So here is this L5, the most promising currently, which has this looking trivial Lagrangian. Yeah, so just if you compare it with this one, this looks trivial. So F mini is as in electromagnetism, but standard electromagnetism doesn't have charge quantization, allows for charge being any real number, while we need integer. And here we interpret this F dual as curvature of dipole field. Thanks of that, the Gauss law counts topological charge of this dipole field. We get built-in charge quantization. Moreover, it also unifies with quantum mechanics and gravity, this simpler term. There is a potential term. We know its properties, but the details are still open. We are searching. We need to search through possibilities automatically. Maybe also there is some more kinetic terms, so that's an open question. And again, artificial intelligence could search automatically for such modifications. So, and it has like 3 parameters in terms of 30. So yes, we should be able to derive 30 parameters from 3 or 4 maybe. So to finally understand, not just new epicycles that doesn't work, so we add more new epicycles and more, but we need this new Copernican evolution, trying to squeeze it into deeper, one level deeper Lagrangian to derive entire standard model and gravity unified already. And this tiny Lagrangian qualitatively seems to give what we need exactly. And the third argument, I think maybe the most important, is that we work later on perturbative approximation. So it's like saying that apple plus apple equals 2 apples. Sure, it is true, but it doesn't say it says nothing about the structure. Yeah, so very similar algebra on particles is this Feynman diagram. So they draw this diagram, say electron is perfect point, but in fact this electron has electric field, magnetic field, angular momentum. So we need to get from this perturbative approximation with perfect point particles into deeper non-perturbative. What is the field configuration represented by this Feynman diagram? So maybe let me show such liquid crystal view that we have. As mentioned, we need to support charge quantization. Why we have one charge but not half of electron, half charge? Yes, because of topology. We have the long axis which performs this hedgehog, one topological charge. We cannot have one half. Yeah, so it has to be one charge. So we have quantized topological charge. They get Coulomb for them. And moreover, there is this angular momentum. Yeah, so there are these memes that spin cannot, that we don't understand spin because it says there's angular momentum, but electron cannot twist. But this is perturbative picture. Electron as perfect point is this perturbative approximation, effective. Deeper there are non-perturbative field configurations. So this rotation is not of point, but of the surrounding field, like here. Yeah. So and here indeed we get the topological charge as electric elementary, and the field rotates. There is angular momentum. So it seems to have all the properties we need from electron. Also, Larmor precession. So this is I think natural candidate, especially for charge quantization for electron. Okay, so we talk about this deeper field. We've given by this looking trivial Lagrangian, but extremely complicated consequences. So yeah, so now having this simpler formula, AI we need to perform simulations like partial differential equations, prepare configuration of particle, then evolve it, try to find the decay of the particle. I'm showing in a moment. And if these models don't work, maybe try to some modification, maybe add some term to kinetic term, maybe modify potential, maybe different type of potential, and finally. And it still doesn't work. Maybe you can look at multiple models made by humans, then try to find better ones, maybe some intermediate, maybe some evolutionary evolution in the population of Lagrangians. So then I think building such environment for tests, then getting the real Lagrangian should be a matter of maybe months or something like that. So I think we are very close. And there are at least two articles we've published in good journals with this kind of approach based on AI, like here for neutrino oscillation. There is agent, try to guess new model, maybe some population, calculate its consequences, and then again test if the consequences agree with what we know, yes, with experimental data. Or this article that exploration of physics model. So we simply have some observations, and we need to find this AI have to find a deeper model which explains these observations. Yeah, and we can automatize it now. Yeah, so test various possibilities, find consequences, make simulations, analyze the simulations, and summarize, and they make loop, maybe improve the Lagrangian, and so on. So I think it's a matter of time to find. So our nature should be governed by some Lagrangian. So I think it's a matter of time to finding it. Yeah, we are on the hunt of the real Lagrangian of nature, the deeper one, but it doesn't have to be the deepest one. So maybe this is just going one level deeper. Maybe there could be another even deeper levels. So. Okay, so here is some summary of these benchmarks current from yesterday. So there is this web page and this address, and you can see that there are these 4 models here. There are more obviously, and there are various properties which it tests. So automatically Fable with making simulations that tests if this model has given property, as we know from physics. Like charge quantization, yes, for topological, this is trivial. Then you can just mass. Then there is very interesting, the Broglie clock. So that's the question, why resting electron has angular momentum, why the fields rotates, why also neutrinos oscillate. Yes, why resting neutrinos oscillate. So it is called recently time crystal, that's an object which is oscillating in the lowest energy state is called time crystal, like electron or neutrino. So to get it, energy minimization should lead to non-zero time derivative, that the field wants to rotate in the presence of its particle. And indeed, in this model, this liquid crystal approach, we get this kind of mechanism. Then some stability, then testing the magnetic dipole moment, angular momentum. And I think the best test is just testing if you get a Larmor precession, that we have this electron being tiny magnet and gyroscope, and it gets precessions depending on the magnetic field. And indeed, it was tested by Fable for at least for this model. So then there is the spin 1/2. It is shown as some magical property that we need to rotate by perform two complete rotations to go back to the original state. Yeah, so that's kind of one of magics of quantum mechanics. But we don't need any magic. So here is the simple diagram that in liquid crystals they get 1/2 spin as topological charge, because while we rotate by one rotation, the field rotates by half rotation. So from this to this, but for some fields like ellipsoid, like rod, this rotation, this is the same. Yeah, so ellipsoid here and ellipsoid here is the same ellipsoid. So thanks of symmetry of the field, we can get this spin 1/2 without any magic. We don't have to rotate twice to go back. We rotate once, the field rotates by half, but this rotation by half is the same field. Yeah, so there is no magic in this spin 1/2. We don't need to any magic. Annihilation is natural for topological charges. Neutrinos with oscillations we also get as for the clock of lepton spectrum. Why you have 3 leptons, so I'll show in a moment. Okay, so let me briefly introduce this liquid crystal approach as the most promising. So there are many experiments. So real experiments with real liquid crystals. So as many screens are from liquid crystals, so they are these rod-like particles which can have these complicated configurations, and they can be these topological charges. It's this one charge, second charge, and they can look what is the distance versus time. Yes, and they get this kind of behavior which can say that this is Coulomb-like. So this way they experimentally got quantized charges, topological as electric, and with Coulomb-like interaction. And there are multiple such experiments, again, well published. So we can get electromagnetism with topological charges for quantization. Also, there are many arguments to treat vortices, knots of topological vortices as nuclei. So I will talk in a moment. So I think this is the main problem why we don't understand nuclei now, because there are this one-dimensional structure. They are called quark strings inside nucleons, but they also should go between nuclei. They should also help with binding, nuclear binding, especially with halonuclei. I'm showing in a moment. So this is from this article, and I think this is very important to really understand nuclear physics finally, because now currently we are just guessing and have some general formulas which we can fit to experiments. Okay, so and electromagnetism is also very similar to hydrodynamics, nearly the same formulas, especially if using superfluid without viscosity. Okay, so let me briefly show some mathematics, the intuition, what's happening here. So as mentioned, the first problem is that the Gauss law, that the standard Gauss law integrates electric charge over some area, and this is the charge inside. But the problem is that this charge can be real in standard Gauss law. One image is integer. So the question is why it is integer. Yeah, and there is topological version of Gauss law called Gauss-Bonnet theorem, and that indeed gets with Gauss law gets topological charge which is integer using this called curvature of this deeper field. Okay, so we have some deeper field. It makes this hedgehog, and we calculate, we interpret its curvature as electric field, and then the Gauss law counts topological charge. So this way, we repair electromagnetism with charge quantization as topological. Yes, by just introducing this deeper field and say that its curvature is our electric field. So now we have this charge quantization with electric field, and now we can also recognize this twist of this field. Yes, so like here that we have these high energy tilts which get electromagnetism, and low energy twists, because this rotation is much cheaper from energy perspective. And turns out we get Klein-Gordon-like equation for it, so it fits well to quantum phase, but with lower energy contribution. And indeed, in QED Lagrangian, indeed we have electromagnetism with high energy contribution, and this quantum phase dynamics with low energy contribution, very low. This H bar, so it's very, very weak effect, but still crucial in many situations. So now we have these tilts, high energy tilts for electromagnetism, low energy twists for quantum mechanics. And in 4 dimension, we have also for the axis, the temporal axis, like here. So it needs to be much longer. It's much more difficult to activate gravity. So it corresponds to gravity. So this 4th axis needs to be much longer. if it would make Hedgehog, this would be like black hole. So it's very difficult to make Hedgehog from this long axis. So what is expressed here by higher energy contributions in our Lagrangian, and its dynamics are the three boosts. Yeah, so here we have the high energy tilts for electromagnetism, low energy twist for quantum mechanics, and Gordon, and here we have high energy boosts. So it's very difficult to locally boost the light cone, you can say. And we can get second set of Maxwell equation. It's called gravity electromagnetism. This is what was verified by gravity probe B. So it's some different formulation of general relativity. Maybe. Okay, so we very simple formulas. We get unification of electromagnetism plus quantum mechanics plus gravity, plus with topological defects we get topological charge plus topological vortices for quark strings, and together they beat nearly all the particles. So very simple view on the entire physics, but simulations are extremely complicated. So here are some simple calculations written by this simple code. So this is simplified of Coulomb interaction. Yeah. So why we have two charges? Why they have this 1/r square attraction and repulsion? What is given by Coulomb potential? So what we do? We take these two topological charges, opposite or the same, in various distances, and for each configuration calculate the total energy. What is done by integration of Hamiltonian. And so here is the Hamiltonian, the sum of square of curvatures, as mentioned. Here is the integration, and it led to this behavior, this orange line or the blue line, depending if the same or opposite. And this is exactly turns out exactly as Coulomb. Yeah. So just from this assumed, again from this simple looking Lagrangian, we just got Coulomb for quantized topological charges. It also has Lorentz invariant, so from Coulomb you can get a magnetism, so we get entire electromagnetism already, and including also the boost, we get gravity, twist, we get Gordon for quantum mechanics. So super simple formula, but simulations are extremely difficult. Okay, so we get Coulomb manually written in Mathematica, and now with Fable we can do much more, like decay of muon. Yeah, so here is from Fable maybe a week ago. So first question: why we have three leptons? Yeah, so we don't have just electron, as mentioned. It should look like this, but in nature there are three leptons. So it has to be Hedgehog. Yeah, so but in 3 dimensions we have three axes. So we can be Hedgehog of this axis or this axis or this axis. So we have three ways to build Hedgehog. And Fable first tested that starting from such Hedgehog one of the three axes, we can get to local energy minimum. Yeah, so local for muon and tau, the heavier ones, and global for electron. Asymptotically, they have still this topological charge, so asymptotically they look like just point charge. Yeah, so electromagnetism is the same, electric field is the same, just they have different energy because of different configuration, especially in the center. So it found the configuration for the three leptons. Then we need to find them decay. Why the heavier configuration like muon decays into electron? So it has to kick. So it was in local minimum. It has to be kicked, and now after kicking, it got from the simulation this ring evolution shown here to electron, the lowest energy state of given charge. Yeah. So if you have non-trivial energy, non-trivial charge, then minimization of energy should lead to electron or positron. And moreover, there are these topological vortices required by this. It's called Haley-Bohr theorem that we need also topological charges very light here. So if it quickly twist this field, this energy of this twist should be released, eject these vortices. And these closed vortices here are interpreted as neutrinos. There are many arguments for that. And then it goes to electron. Here is the simulation. So we start, the scale is completely different here and here. So it starts with this very heavy muon. And now it releases this energy and goes to electron and releases these topological vortices. And the Fable was able to perform this simulation and analyze the behavior. So while mainstream basically works still on this formula. Yeah, so that we have One abstract point is going to another abstract point and two other abstract points. Yes, but there are field configurations. So now we can ask for, they say, non-perturbative picture. And finally, we are able to make this question and get very concrete field configurations and the evolution which can be simulated. Yeah, so these are difficult simulations, but now I think they are in reach. So next question, maybe more practical, are the nuclear physics. Yes, as mentioned, there is this MC effect, which says that nuclei as bags of quarks completely don't work, and the people claiming deeper physics, lattice QCD, they focus on neutron, proton, no nuclei. Deuteron is too difficult for them. Yeah, so they can say nothing about larger nuclei, nearly. Okay, so and the most interesting nuclei, and maybe it sounds very non-trivial, are so-called halonuclei, like lithium-11, that it has core and two neutrons in very large distance, like 5 femtometers, while nuclear force is like 1 femtometer. So what binds them in 5 femtometers for like milliseconds? So it's extremely long time. And moreover, they need three-body forces, and they call it Borromean, like here, that if you cut one, then all are ready. So this Borromean needs one-dimensional structure. Yeah, so there are many strong suggestions that we need some one-dimensional structures connecting this core and the halos. And indeed, in nuclear physics, they call it quark string QCD flux tube. Yes, that between quark and anti-quark, there is some one-dimensional structure of very high energy. And in this topological view, we can see them this way, that we have this topological vortex, and we perform this fractional charge excitation of this vortex. I will show in a moment why. So it bends the charge quantization, which is topological here, and this bending leads to some conflict between them, and this conflict is very costly. So it in QCD, there's additional this very high energy, this 1 GeV per femtometer energy here, which can be explained by just this very local bending of charge quantization. Yeah, so we can understand everything here as field configuration, why mainstream only seeks perfect points, magical points, and some very magical picture here. Why just asking, we can get a lot here. Okay, so here is the final slide. So this is just the beginning. We need better simulations. We need the details of the Lagrangian, maybe better Lagrangian, additional terms, and finally to simulate various situations. So here are some candidates for other particles, as mentioned, the 3 leptons, 3 neutrinos. Then we need nuclei, as there are many arguments that there are knots of some one-dimensional structure, stable topological vortex. So, for example, the simplest knot we can do is this one. So one vortex inside and one around. So we can see that the vortex around deforms the central configuration and deforms toward hedgehog. And hedgehog for us is elementary charge. Yeah? So proton can just enclose this hedgehog, while neutron has to compensate this enforced charge. And this compensation is costly energetically. So this way we can explain why neutron is heavier than proton, and also that it is known that neutron has positive core, negative shell. So we can get proper charge configuration of neutron, explain why it's heavier than proton. Then for deuteron, we have two baryons, both require this charge. So we have plus, minus, plus. So it is electric quadrupole moment. And indeed, it is known experimentally that deuteron needs to have electric quadrupole moment. While mainstream that cannot answer this question. So the charge I have talked with lattice QCD people about the charge configuration of neutron. They know nothing about deuteron, even worse. So there are these like lattice QCD people are supposed to get deeper understanding of nuclear physics, but they cannot answer the simplest questions about nuclei, like like moments which are measured in experiments. Then we can find the beta decay, which should be very similar to this decay of muon. That now we have neutron, and it releases energy again as neutrino and electron, and this should be concrete dynamics of field. We should be close. So to finish, it doesn't have to be the final level, because, for example, there is a problem that we need to explain still, why there are so huge differences between electromagnetics, quantum mechanics, and gravity. So I suspect there should be even deeper level, from which we should derive this deeper level. We focus on here. So we still a lot to do. So thank you for attention. Generally, the help is needed. One can add more on model to this open wave. Also welcome additional these benchmarks. Yeah, so this is, I think, the first benchmark kind of arena for models. Yeah, so let's there are lots of these theory of everything claims. Let's gather them and vigorously verify. Maybe one of them is right, and if not, we could literally train AI and find the best pieces of them and build a better model, maybe to finally solve physics, at least go one level deeper. Thank you for attention. So I think this is very close.